Hello and welcome back. In the last video, we looked at IP version 4 concepts and we also looked at one example of subnetting. In this video, we are going to continue to focus on subnetting and we'll practice 3 more examples. I hope you still have a pen and a paper handy. I'm confident once we complete these examples, you're not only going to start liking subnetting if you haven't already, but you're also going to become a master of subnetting. Having said that, let's now look at the first example. The first example is to divide 172.10.0.0/16 into 10 networks. Remember the first example that we looked at was 192.168.1.0. That was a class C IP address. This one is a class B IP address. The first step says convert the subnet mask into binary format. The original subnet mask that we've been given is a /16, which in decimal would be 255.255.0.0. Convert this into binary and you'd get, that's the binary subnet mask, and that's the first step. Step number 2 says determine the number of host bits to be borrowed, and the formula for that is 2 power x is greater than or equal to the required number of subnets. So the formula would now become 2 power x is greater than or equal to 10, which is the required number of subnets. We need to find the value of x that will satisfy this equation. Let's start with x is equal to 0. X is equal to 0 will give you 2 power 0, which is 1, which will not satisfy this equation. X is equal to 1 will give you 2 power 1, which is 2, and that is less than 10. X is equal to 2 will give you a value 2 power 2, which is 4, and that is not greater than or equal to 10. X is equal to 3 will give you a value of 2 power 3, which is 8, and that also does not satisfy this equation. X is equal to 4 will give you a value 2 power 4, which is 16, and that definitely satisfies this equation. So the number of bits that we need to borrow is x is equal to 4. That's step number 2. Before we move to the next step, let's look at the new subnet mask. Now the first 16 bits are already occupied with network bits, so we need to borrow additional bits from the host bits, which means we need to convert the zeros into ones, and we're going to convert 4 zeros into ones. So the new subnet mask would look like this. The first 4 zeros have been converted into ones, so the /16 now becomes /20. To determine what /20 in decimal would be, we need to align these bits against the powers of 2. I have the powers of 2 listed here. Let's align the bits. So we have 4 zeros followed by 4 ones followed by 4 zeros, and then we add the powers of 2 corresponding to the ones. So that's 128 plus 64 plus 32 plus 16, and that will give you the value of 240. So /20 is 255.255. The third octet is 240.0, and that is your new subnet mask, my friend. Let's move to step 3. Step 3 says determine the increment. Let me clear the board for a second. We discussed in the last video the increment is the power of 2 corresponding to the least significant bit. Let's align the bits one more time against the powers of 2. The least significant bit is the power of 2 corresponding to the rightmost bit. The rightmost bit in this case is here, and the power of 2 corresponding to the rightmost bit is 16. That is going to be your increment. The last step says add the increment to get new subnets. The original network address that we've been given is 172.16.0.0. Where do we add the increment is the question. We need to add the increment to the octet from where we borrowed the bits. In this case, we borrowed bits from the third octet, so we're going to add the increment in the third octet. Let's start doing that. Adding 16 to the original network address will give you 172.16.16.0. And then you have 32.0, 48.0, 64.0, 80.0, 96.0, and so on. How many new subnets will you get? We discussed this in the last video that total number of new subnets will always be a power of 2. In this case, we borrowed 4 bits, so we are going to get 16 additional subnets. We need only 10 and we use only 10, and we reserve the remaining 6 for future purposes. The important thing to remember here is the subnet mask is no longer a /16. For all these new subnets that you get, the new subnet mask is /20, which is 255.255.240.0. That's the first example. Let's now look at the next example. The next example is to divide 124.0.0.0/8 into subnets with 500 hosts. This example is a little bit different. The first two examples had subnetting based on the number of networks. We were given an IP address and asked to divide them into X number of subnets. Here it says divide 124.0.0.0/8 into subnets. We are not told how many subnets, but instead it says that every subnet needs to have at least 500 hosts. I hope you understood the requirement. We don't care about the number of subnets, but all the subnets that we create or all the subnets that we derive need to have at least 500 hosts. The steps for subnetting will remain the same. Let's start with step number 1. Step number 1 says convert the subnet mask into binary format. /8, as you now know, is 255.0.0.0. Converting this into binary would give you, that's the binary subnet mask. Step number 2. Now step number 2 changes a little bit for this question. The original step number 2 says determine the number of host bits to be borrowed. In this case, we are not subnetting based on networks, but we are subnetting based on hosts. So we don't need to borrow bits, but we actually need to fix the bits. Why, if you may ask? We have a requirement based on the number of hosts. So we need to fix X number of bits as host bits so we get the required number of hosts. So the formula now becomes determine the number of host bits to be fixed. We need to fix some bits as host bits so that they remain unchanged, and then we get the required number of hosts. In this case, the formula now becomes 2 power x is greater than or equal to the required hosts, required number of hosts. There's an important thing to consider here. In every subnet, the first address, like you know, is the network address, and the last address, like you know, is the broadcast address. So in every subnet, we actually lose 2 addresses, and that needs to be added here. So the formula would be 2 power x is greater than or equal to the required number of hosts plus 2. In this case, that would be 2 power x greater than or equal to 500 plus the 2 addresses that we lose in every subnet. So 2 power x is greater than or equal to 502. We need to find the value of x that will satisfy this equation. The powers of 2 that we have listed here will make it a little bit easier. 2 power 7 is 128. So we know x is equal to 7 does not satisfy this equation. X is equal to 8 will give you 2 power 8, which is 256, and that is not greater than or equal to 502. X is equal to 9 will give you a value of 2 power 9, which is 512, and that's what we're looking for. So x is equal to 9. So we now need to fix 9 bits as host bits. Let me clear the board for a second. Alright, so we determined that x is equal to 9, and we need to fix the last 9 bits as host bits. The last octet has 8 bits, and then we have one more bit, which is the 9th bit, that needs to be fixed as host bits. The remaining bits can now be converted into network bits. So now the new binary subnet mask would look like this. You convert all these bits into network bits, second octet, and in the third octet we need to leave the last bit as a host bit and convert the remaining bits into network bits. and the last bit still continues to remain a host bit, and the last octet is completely zeros. That's the new binary subnet mask. I hope you understood this, my friend. We now have 9 bits in the new subnet mask reserved for host bits. And now if we calculate using the formula, the total number of host addresses would be 2 power h minus 2. We have 9 bits as the host bits, that would be 2 power 9 minus 2, 512 minus 2, 512 minus 2, 510 host addresses per subnet, and that's exactly what we're looking for. So let's now look at the new subnet mask. We originally had a subnet mask of /8, which now has become let me count that quickly. You have the first 8 bits plus another 8 bits is 16, 17, 18, 19, 20, 21, 22, 23. So your new subnet mask now has become /23. To find the decimal subnet mask, let's align these against the powers of 2. That's 7 ones followed by a 0. And then we add the powers of 2 corresponding to the ones. So that's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2. And that will give you a value of 254. The first octet is completely ones, so you have 255. The second octet is also ones, so that's 255. The third octet is what we calculated as 254.0. That's your new subnet mask, my friend. Let's now look at step number 3. Step number 3 says determine the increment. As you and I now know that the increment is the power of 2 corresponding to the least significant bit. We already have the bits lined against the powers of 2, and we can see that the power of 2 corresponding to the least significant or the rightmost bit is 2, and that is going to be our increment. Step number 4 says add the increment to get the new subnets. Now in this case, we modified 2 octets from the original subnet mask. We were given a /8, and this is the original subnet mask. We changed the entire second octet to ones, and then we also modified the first 7 bits of the third octet. So where do you add the increment? We will add the increment to the octet that has the least significant bit. The least significant bit in this case is in the third octet, so we'll add the increment in the third octet. The original network address that we've been given is 124.0.0.0. Adding the increment, which is 2, to the third octet will give you 124.0.0, 124.0.2.0, 4.0, 6.0, and so on. How many such new subnets will we get? The original subnet mask was /8, and the new subnet mask is a /23, which means we actually borrowed 15 bits. The total number of new subnets will be 2 power 15, and I don't know what that value is. That must be a huge value. The total number of hosts per subnet will be 2 power h minus 2. In this case, every subnet will have the last 9 bits reserved for host bits. So the total number of hosts per subnet will be 2 power 9 minus 2, which is 512 minus 2, and that is 510, which satisfies the original requirement of 500 hosts. Isn't this whole thing really fantastic? I find it really fascinating that we're given an IP address, we perform some calculations, and we divide that into multiple subnets. I hope you're enjoying this as well. Let's now look at the last example. The next example says, which subnet does the IP address 200.1.1.10/29 belong to? If you look carefully, this IP address already belongs to a subnet. We already know that Class C IP addresses start from 192.0.0.0 all the way up to 223.255.255.255. This one is a Class C IP address, and a Class C IP address has a default subnet mask of /24. This one has a subnet mask of /29, which means the subnetting has already been done. We've been given a subnetted IP address and we are told to find out the subnet to which this IP address belongs. Even though this sounds a little bit different, the steps are exactly the same as we've been doing all along. So let's begin with step number 1. Step number 1 says convert your subnet mask into binary format. /29 in binary format would look like this. That's the first octet, second octet, third octet, and by now you have 24 bits. We need 29 network bits, which means there's additional 5 ones in that subnet mask. That's 5 ones and 3 zeros. That's your binary subnet mask. The second step says determine the number of host bits to be borrowed. Now remember, we are not doing subnetting here. This is already a subnetted IP address, and we can say that by looking at the subnet mask. A class C IP address should have a /24 subnet mask, but here the subnet mask is a /29, which means the subnetting is already done and we do not need to borrow any bits because the bits have already been borrowed to perform subnetting. So we can skip step number 2 completely. Let's now move to step number 3, which says determine the increment. To determine the increment, like always, we'll align these bits against the powers of 2. So that would look like this. The increment is the power of 2 corresponding to the rightmost bit. That is 8 in this case. So the increment is 8. The last step says add the increment to get the new subnets. Before we start adding the increment, we need to get the first network address. The first network address in this case is 200.1.1.0. It's not a 10, it's a 0. That's the first network address. And now we need to add the increment. The increment should be added to the octet which has the least significant bit, and that's your last octet. So we need to start adding the increment to the last octet. Let me get some space here. Adding the increment to the last octet will give you 200.1.1.8. You continue adding and you get 200.1.1.16, 200.1.1.24. Looking at the original IP address that we've been given, 200.1.1.10, and looking at the subnets that we've derived, we know that IP address definitely belongs to one of these subnets because we've gone all the way up to 200.1.1.24. Let's look at the ranges of these subnets. 200.1.1.0 and the next subnet starts at 200.1.1.8, which means the range of this subnet is 200.1.1.7. That's the first range, or that's the first subnet. The next one is 200.1.1.15 because this one starts at 16. Look at the IP address that we've been given, 200.1.1.10. That definitely fits inside this range, 200.1.1.8 all the way up to 200.1.1.15. So the question was, which subnet does 200.1.1.10/29 belong to? The answer is this one here, 200.1.1.8/29. That's the subnet to which that IP address belongs to. That was really simple, isn't it? We've now completed all the examples of subnetting. I found it really interesting to teach you subnetting. I'm really confident that you now find subnetting to be an interesting topic. Just to do a quick recap, we looked at 4 different examples of subnetting. In the last video, we started with a Class C IP address. We then moved to a Class B IP address. Both these examples were subnetting based on the number of networks. We then looked at a Class A IP address, which was 124.0.0.0/8, and this one was based on the number of hosts. And finally, we looked again at a Class C IP address, but in this case, we were already given a subnetted IP address, and we had to find the subnet to which it belongs to. In the next video, we are going to look at IP version 6. We'll take a look at the IP version 6 address format. We'll take a look at the rules for writing IPv6 IP addresses. We'll take a look at the different addresses and address types. And finally, we'll also take a look at IPv6 subnetting. That's the plan for the next video. I really enjoyed talking about subnetting with you, and I'm excited to see you in the next video. I'd like to thank you for watching.